Hey y'all, in this lesson we are going to compare linear and nonlinear functions. So we wanted to simply be able to do that. I can compare linear and nonlinear functions. Remember from last time that if a graph of a function is a straight line, it is a linear function. And if the graph of a function is not a straight line, it is a nonlinear function. Our essential question is, how can you compare two functions? In example 1, we are going to compare a linear function and a nonlinear function. One thing that we know is when we see the graphs of these, one will be a straight line and the other will not. A square with side length s is shown. The table shows the relationship between the side length and perimeter of the side as the side length increases. The graph shows the relationship between the side length and area. How do the two relationships compare? Well, let's take a look. Here is the table that is showing the side lengths and the perimeter. We see that each time we increase the length of the side, the perimeter increases by 4. This relation is a function because, again, if we know the side length, we know the perimeter, we're not going to suddenly have a different number. It has a constant rate of change because it's changing by the same amount. So this is a linear function. Here is the graph that shows side length and area. We can see that this relation is a function as well because it passes that vertical line test, but it does not have a constant rate of change. It is a non-linear function. So if we saw this in a table, we would see that going up from 0 to 1 goes 0 to 1. But then going from 1 to 2, the area goes from 1 to 4. And then from 2 to 3, the area goes from 4 to 9. And from 3 to 4, the area goes from 9 to 16. So it's not changing by the same amount each time. Both of the relationships are functions. Perimeter and area are functions of the side length. In example 2, we're going to look at two linear functions that are represented and compare those. So now looking at comparing two different linear functions. We can see the equation in function A, and from our equation, we can note that the constant rate of change is 2. The slope is 2. And we can see that the initial value is -3, or the y-intercept is at -3. On function B, we notice the initial value is at 7 because this is the y-intercept where the graph starts. We also notice that the constant rate of change is down 1 over 2, so -1/2. So we can compare these directly and say that function A has a greater rate of change because 2 is bigger than -1/2, but function B has a greater initial value because it starts at 7, where the function A would start at -3. So we can talk about and compare their rate of change and their starting points. You try it with this one. What are the different properties and how do they compare for function 1 and function 2? In our final example, we'll take a look at a word problem that uses two linear functions for comparison purposes. An auto assembly factory needs to purchase new welding robots. The factory manager has information on two different models of welding robots. The welding rates for each model are shown below. How do the welding rates for the two robots compare? So rates, we want to be looking at the slope or the rate of change, okay? So this is an example where we are given the same information, their rates, represented in two different ways, a table and a graph. And we want to be able to compare them to figure out which is the better model. To find the welding rate for each robot, we want to first look at the table. In the table, we see our outputs or our y values, the number of welding tasks, and our input or our x values in time. We know that we can use our slope formula to find the rate, and so we just select 2 points on our table, and we will subtract the outputs or subtract the y values, 52 minus 20 over 20.8 over 5 minus 2. Do that simple math, you get 31.2 on top and 3 on bottom. Divide it all the way out and you will get 10.4. So the constant rate of change, or the welding rate for the Model T1000, is 10.4 tasks per minute. Looking at the Model GNX 007, we want to look from one point to the next, and we can see that as we look from one point to the next, it's going over 1 and up 11.2. Now that would not be easy to tell straight from the graph without knowing exactly where those points are, but we are going to trust the depiction here that it is going up 11.2. The other part we want to look at is the initial value. At 0 minutes, each robot has performed 0 tasks because we haven't turned them on, so the initial value is 0. So this is a proportional relationship because it's starting at 0. Now we can directly compare the two models. The data for the model GXN007 had a greater constant rate of change. It was 11.2 versus 10.4. So it can complete more welding tasks per minute than the Model T1000 robot. So if speed is what we want, we're going to go with the Model GXN007. With those same two models, if we add a third model that has a welding rate represented by this equation, how does it compare to the other two? Is it faster than both of them, slower than both of them, or somewhere in the middle? Reminder that the rate of change will be the slope. And how can you tell a slope from an equation? Summarizing, comparing linear and nonlinear functions. You can compare functions in different representations by using the properties of the function. For example, we can compare two linear functions by talking about the slope and the y-intercept. This is the constant rate of change and the initial value. Remember that we can compare linear and nonlinear functions by simply the fact of whether or not they create a line when they are graphed. Your next steps are to turn in your 4.3 notes, complete your Build 4.3, and take your 4.3 Mastery check. Then continue on to the next lesson. Good luck!